This is the ROS Developers Podcast, episode 124.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and today I would like to dedicate this episode to all those ROS developers out there that are thinking about using ROS in their drones, or maybe trying to apply their path planning techniques into drones. So if you are thinking about using your favorite framework for robots into drones, this episode is dedicated to you. And today we are going to talk a lot about drones and also ROS, and maybe some things that are not ROS for drones also, but anything that is related to the drone world with an expert, and you are going to enjoy it and get a lot of insights for your programming of your drones. But before going into that, let me tell you about the robotics masterclass that we are developing. So we have developed a program which we call the Robotics Developer Masterclass, where we are teaching people from zero skills to become a robotics developer. That means a person who can program robots in the wild, learning all the skills that are required for that. So we just started the second batch of this year, and it's fully enrolled. So in case that you would like to join, there is a waiting list for the next batch. Okay, but let me tell you a few things about this program. It's about 1,000 hours of learning, and there we are going to teach you. It's a flexible way of learning, so you can learn by yourself, going at your own pace. We recommend you, and we have prepared a plan to be done in 6 months, but it depends on you, so you can take longer if you want. And those are the phases that are included into this masterclass, which bring you from novice into an expert, and even to be close to get a job, because we are including an internship at the end of the program, an internship with partner companies, robotics companies along the whole world. So we start from the novice, teaching you the basics of programming and the basics of ROS. Then we go with more advanced skills in robotics, like navigation, perception, manipulation, controllers, everything. And in each one of those sections, you are going to be practicing with simulated robots and real robots, like you can see here on the screen. So those real robots are real robot labs that we have here in our facilities in Barcelona. You will connect remotely to our labs and then practice with those robots. On the third phase, you are going to learn about the basics of robotics theory and using another real robot lab, ROSbot XL based. Then, in the final phase of number 4, you are going to be learning about the development tools that you need to work in a company. It's about continuous integration, Docker, and unit testing, and so on. So this. And then finally, at the end, you will have to create a project in our Starbot robotics cafeteria, where you will be applying all that you have learned into this cafeteria environment. And then at the end, we provide you an internship that you can use as a practice in a real company of your new skills. You can check our list of available companies, partner companies, in our webpage. Okay, so having said that, now let's go to the meat of the episode. Let me introduce here today the person that is with us for this interview. So, let me introduce you, Kimberly McGuire. And Kimberly is a robotics engineer at Bicraze, where she develops the tools that connect the Crazyflie with the community of developers. She also has received a PhD in 2019 with a thesis about swarm exploration with pocket drones. So she is here today to talk about drones and ROS. Welcome to the podcast, Kimberly.
Thank you so much for inviting me, Ricardo. I'm happy to be here.
My pleasure, my pleasure. But I have so many questions because drones and ROS is a subject that is a little bit obscure. So just a few people is working on this. But before going into that, let's clarify some terminology because it's not clear for us, you know. Then the one point will be the first one. Can you define it? What is an UAV?
Of course, yeah. Well, the abbreviation stands for unmanned aerial vehicle. So it's a very, very broad term. It practically stands for any aircraft that doesn't have any pilot, crew, or passenger on board and still able to keep flying in the air. So that also means it's not maybe not the smaller quadcopters that maybe you have in your mind, but it's of course also the bigger drones. It has a very like military history, of course. That's kind of where it also originated. But of course, these days, drones are pretty much, or UAVs are being used practically everywhere in terms of surveillance, in agriculture, for shows. Yeah, you name it.
Okay. So that would be like the big category that comprises other subcategories, by which one of those is drones. So drones are a category of UAVs? Or are equivalent?
No, it's the same.
It's the same thing.
It's the same, I would say. I think UAVs and drones are used interchangeably. I would say perhaps like in academia research, people maybe would like to use UAVs a bit more because drones is a bit more related to like the military background, but it pretty much means the same, exactly the same thing.
Okay, and then the third term will be quadcopter. Please tell me yes. That is the subcategory, right, of drones. That would be the quadcopters. Is that right?
That is absolutely correct. That's kind of like a subdivision or type of UAV. So quadcopter, kind of what the name already says, is a aerial vehicle that has 4 motors and 4 propellers and uses that to, keep itself in the air.
In the air.
But I think it's also kind of good to know that there's kind of also, you have subdivisions that you can based on type, like quadcopters, but you also have like fixed wing UAVs and flapping wing MAVs, and there's like, there's a whole bunch out there. But I think also people like to also make subdivision based on weight. So you also have terms like micro aerial vehicles or nano aerial vehicles as well, which means it's like, for instance, anything that's less than 250 grams is a nano aerial vehicle, which is, for instance, like the Crazyflie, and anything that's larger than that is, or like weighs more than that, that's a micro air vehicle, and then you have all kinds of different terms for that as well. Wow. So yeah.
Okay, so that I see that this is a complete world there. I had no idea about that, and then it's so you have mentioned the Crazyflie, and we are going to clarify what it is because maybe some people of the audience doesn't know what is this. But before going into that, so how do you program? How a program runs in a drone, in a quadcopter?
Yeah, it's kind of like an it depends question. Like, it really depends on what kind of size the quadcopter has, what kind of computer it can carry. So like smaller drones usually have like microprocessors. So that's usually a C-based programming language based firmware. C or C++. But bigger drones, they can usually carry a bit more than that, and they can carry like something like in one of the latest like Raspberry Pis or Jetson Nanos, and then you can kind of like program on it like on any Ubuntu computer. So that is kind of like of course the thing. But usually with drones, you always have kind of a combination between a flight controller that takes care of like the low level control stuff, and something that does like more of the higher level autonomy, like a companion computer.
Which is this companion computer, it on board the quadcopter, or it's in an external computer outside the drone?
It can be both.
Okay, great,
Yeah,
great.
it's definitely something also really determined on the application and the size of the drone. I think also that's like they also call the companion computer if that's a computer that is just on your desk and that is directly communicating with your drone and controlling your drone at the same time. But of course, like in the field of robotics, you would like to see things a little bit more on board and integrated. So
Yes.
like the ideal case is to have a companion computer on board. But of course, since a quadcopter has it has limited lift power, it has limited battery. So sometimes choices have to be made, let's say.
Okay, okay. Then you mentioned two computers in the two systems. The one is the companion computer that you mentioned, which would be like the one that runs the program that executes the task. That like decide whether to go straight and then turn here or follow a certain person or a certain pattern or whatever. That would be the code executed by the companion computer. But then you mentioned another computer, the basic one, which is, how did you call that one?
The flight controller.
The flight controller. So what is the mission of this flight controller?
It's to make sure that the UAV doesn't crash.
Okay.
No, it deals actually with like the lower level or position-based control, and usually also a bit of sensor fusion. That is actually meant for either what they called attitude controls, able to stably keep its roll, pitch, and yaw stable, because a quadcopter is an unstable system actually.
Yeah, because
so that needs to be So that needs to be stable, and that's usually also done by means of the going into sense like the IMU. However, a lot of flight controllers also provide position control, so like one layer on top, so that they are also able to kind of control X, Y, and Z position as well. So that is kind of like at least like the goal. What the flight controller is that at least you're able to make it fly stably, and it's able to stay at one position. It's usually not meant to really give any like higher level commands on that. However, as I've been usually the Crazyflie is very computational limited system. You can also do autonomy on board of a microprocessor as well. But the usual.
Goal.
It's not necessarily the goal, but if you're limited in processing power, you get creative, let's say.
Okay.
And that is definitely possible. But I think definitely if you're a beginner, if you're just starting out, it's easier to kind of separate the low level control or the position control on the flight controller and the actual mission control or autonomy control on the companion computer, or for instance off board of your own computer. That's of course also possible.
Okay.
Yeah.
Okay, then this, just to rephrase, if I have understood, then this controller, what it does, it's because the let's say it's a quadcopter, then it has 4 motors that are running, each one is running at its own way, so you have to coordinate those 4 in order to make the robot just stay at one given altitude that you want. So and keep it stable there, and that's not an easy task. So, and so you have to have a microcontroller there just dedicated to maintain this position, to be able to maintain the position, the altitude at which you want the quadcopter to be there. So that would be the mission of that basic control computer, right?
Yeah, that's I think the main purpose of it indeed. Yeah.
Okay. Okay, and then when we buy a drone, do we have to program all this into the drone, or does the drone already come with this altitude or this basic controller?
So there's actually, luckily, you don't have to do it all by yourself these days, so that's great. They are what they call autopilot software suites or firmware suites that you can use. So there's a couple of options there. Peaks4 is a very common option, but you also have things like ArduPilot. Paparazzi UAV is is also one that has been existing for a long time. And of course, like, yeah, at least for the Crazyflie, we have our own in-house developed firmware where, and pretty much all of these kind of already provide all the controllers on like the low level and position level already, and already have like some kind of basic or good functioning Kalman filters, extended Kalman filters that's able to do like all the sensor fusion on board. And of course, all kinds of things to make sure that it's able to communicate that well to the ground station, which is on your computer, or to perhaps like a companion computer that's, yeah, in any form possible, let's say. So those are luckily the options, so you don't have to start from scratch.
Okay. Okay.
That is for quadcopters, though, I would say. Like if you're going to do something fancy like flapping wing MAVs or monocopters, that's a different story. Then
But
you
the,
probably have to
in which
start.
sense? In which sense is different? Is that in the sense that we have to develop this controller for ourselves by ourselves?
Yeah, you usually would need to like develop like some kind of low-level controller of for instance, like with quadcopters you have some kind of standard motor mixing that you can say like, okay, this propeller rotates counterclockwise and this one does the other way around. So like if you have a Ph.D controller that has like the attitude outputs, then if you mix, then you have a couple of formulas that you're able to translate that to commands for each motors. If you have like a special vehicle that has three motors, let's
For
say,
example.
or just one, or it like rotates around like a monocopter or like have wings, like, you know, and like a dragonfly, then, you know, that part is something that they probably have to implement themselves, or perhaps there's not that many well-tested options out there. But if it's a quadcopter, or a fixed wing even, I would say you're pretty okay still.
Okay, okay, but in none of those things, ROS has entered the picture yet. So this is low-level programming and direct access to the hardware. So then, at which point do we have to, can we use ROS in any of those quadcopters? So what do we have to use? We have to use the companion computer to install ROS somehow there, and then have some drivers that connect to this controller so that it can send commands to the controller. Is that how it works?
Yeah, that's pretty much like how it works that's kind of the most common way how to do it at this moment. So you have the companion computer, you can install ROS on it, especially if it's like one of the latest Raspberries or Jetsons, that is like quite easy to do. And then you just have to make sure that you have some kind of communication with the flight controller. Like either you have like a USB connection that makes things a little bit more easier, but sometimes you have to go a bit more lower level, like UART connections and things like that. And at least for the regular autopilots, you have something called MAV-Link, MAV Link, which is a group of kind of standardized messages that they have a ROS package for, so they're able to kind of communicate that one another. However, I am aware, like I am not a, like for instance in the peak, I'm not a very, like, you know, very in-depth Peak4 developer myself, but I know that they are working on kind of closing the gap. So like to put a little bit more of like the ROS communication system on the flight controller itself. So it's a bit more of a seamless integration of topics and services already from like the communication with the flight controller. So yeah, so that's at least like what I know, but that might be still that's still needs to come to stability, I would say. And I would also like to point out like the micro ROS. I don't know if you've heard about that
Yes,
project. It's
micro
like by the
ROS.
yeah. So so they are doing really cool work with also, and I think also that is kind of like also kind of the base that they would like to use to have at least the microprocessors on the flight controllers to be able to do more ROS stuff, let's say.
ROS, yeah. So
Yeah.
it's like putting ROS natively into the controller computer directly.
Yeah, exactly. That's able to already provide the right, like, you know, the right format of the communication that ROS is already able to tap in right away. They have actually a really nice eProsima, they're like I think
The
also a
company?
Spain-based company.
Yes.
They provided a really nice example with micro ROS on a Crazyflie actually. So
Ah.
that's pretty cool.
Okay. Well, so
Yeah.
okay, so I have many questions here yet,
Yes,
but
of
let's
course.
go. Let's go with the crazy fly because you are mentioning already. So
Hmm.
let's see. So what is the crazy fly?
Yeah, the Crazyflie is a small drone that's developed by my the company I work for, Bicraze. So there's a company in Sweden. And yeah, it's a very tiny quadcopter. It fits in the palm of your hand.
Yeah, it's
I
very
don't know if
cool.
I. So it's only 25 grams. So it's very small. And it was kind of like yeah, it was like initially developed to be kind of like an Arduino with propellers.
Okay.
So it was a bit more for like, for instance, like the hacker community to do some really cool stuff. But now it's kind of the development has been more focused on education and research. So
Mhm. Okay, and then this is the uh, quadcopter that your company is developing. And uh, in this project, what is your role? What are you developing for that project?
so currently we have already kind of a set of like software tools and like firmware that we've developed in-house. And my role specifically is to kind of like be the glue between the Crazyflie and the company and the rest of the community. So making tools that's for them easier, for instance, like, making it easier for them to integrate already in their existing ROS projects, for instance, or for instance, what I'm working on right more today is simulation. So that they're able to kind of also try out their ideas before they actually start flying. Um, so and that's kind of my like, building the tools, building the glue between us and the community.
Okay, but and then in any of those steps, are you using ROS or no? Yeah. Okay.
Yes.
Yes.
Yeah,
Yes.
that is I think one of the major tools that we want to use to for that connection.
Okay.
We are close. We're close collaborating with like TU Berlin with Wolfgang Hoening. He made a package called Crazy Swarm, and they're like busy with the ROS 2 port, and we're
Ah.
helping out also with maintaining that. And yeah, the hope is hopefully that we will have like an official Crazyflie ROS 2 node soon. There is already a ROS 1 node that
Okay.
works, but there to have an updated ROS 2 node to easily communicate with the Crazyflie.
But any date that you can give us for that?
Not
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 yet.
yet.
Okay.
Let's say we wanted it yesterday.
Okay. Okay. Okay.
Unfortunately,
So
some things and some other obligations got in the way. But like next year, like yeah, things really have to go wrong for us not to have an official ROS 2 node somewhere like in the before the summer next year. But don't
okay.
don't put my word too hard on it. But yeah,
Okay. Yes.
but
Okay.
I
What a
do feel
pity.
that we should have had it yesterday already. So
Yes. Yes. Exactly. Because then we can do a lot of exercises for with the students, for example. But as you mentioned about
absolutely.
education, then we
Hmm.
can make them practice. For example, in our academy, we use the Talkbot 3, which is a small robot, wheel robot, and that's very cool. But what if we could use also the Crazyflie? That would be awesome for them to see the robots moving around and flying and crashing and all that. That
Hmm.
would be awesome. But in order to prevent that when crashing, they break. So you are using simulations, right? First,
Hmm.
so you test in simulations. And which simulators are you using? First?
Yeah, currently I'm like full on into webbots. So yeah, I have used Gazebo in the past before, and that's also a great simulator for aerial robotics as well. But no, currently it's webbots mostly.
Mm-hmm. I have seen your presentation of Webots with the simulation of the Crazyflie. And okay, then Webots is also integrated with ROS, ROS 1
Hmm.
and ROS 2. So if people want to use the simulation of Crazyflie in Webots, they can also use it with ROS 1 and ROS 2 in there.
Yeah,
And
that's actually easy to do. Like I'm like the very next part of the pipeline is to have an official ROS 2 node for webbots for the Crazyflie model. So that's very close.
oh,
So that you're able to just do like an sudo opt install like webbots ROS2 Crazyflie, and that you're able to already do that. But it's like, it's already quite easy to implement yourself. They have some really nice tutorials on that as well. So it's
And
but
do you have a
sorry?
repo? Do you have a repo where?
Yeah, we have a repository for that. Let's see. Yeah. But
Okay.
I guess like what I also like, of course, like Ross is we're here at the Ross Developer
Yes.
podcast. So of course, like Ross is awesome, and I love Ross.
Okay.
However, I do like Webbots as well because it also works quite well as a standalone simulator too.
Yes, yes, yes.
Yeah,
Robotics is awesome. Robotics
yeah.
is excellent, and I'm a friend of Olivier actually. And there are some parts in Robotics that I developed. The ones for the Ivo robot in the past, so many years ago. So I love it. Also, Robotics is excellent. It's excellent. And the only thing is that it's not so common to be used in the ROS community, but it's completely supported in ROS 1 and ROS 2. So community of there, if you want to try a super cool simulator, you can use Webbots. And then I wanted to, I will ask you for this Git repo, and then I will put it in the links on the show notes.
Yes, of course, yeah.
So they can
I
check.
think for the Webbots ROS2 example, there is like more of an experimental GitHub repository, but I will also show that with like just the simulation repository as well. So
Okay, excellent, excellent. Well, I don't know. let me continue with the Crazyflie, because we have been jumping now, and now I kind of lost where I have to go, but it's okay. It's okay. So that podcast is the purpose, to have some chat here and enjoy and learn something. So why did you create the Crazyflie? What was its purpose? Why so tiny?
why so tiny? Yeah, that is actually a very good question. Like, because we of course like have three founders of Bicraze, and they have been with the company for almost like over 12 years. And they started with like the Crazyflie 1, and now we're the Crazyflie 2. And back then, they wanted to make a development board, let's say, that is just more than only something that you will just plug into your computer, but something that actually does something. So that's why they came up with the idea of making a quadcopter out of it, and a very small one. At that time was the smallest development quadcopter that you can actually get 12 years ago.
Okay.
Now, like, the reason why it's still so small, why we haven't really made it bigger yet, is just it's safe.
Yes.
It's super safe. You can just like, we also have seen courses where it's definitely during the COVID period where they just like, they grab a bunch of Crazyflies with flow decks, and they give them to their students to do like, their practicals at home, because like it's much less of like a drama if a very 25-gram Crazyflie hits against your face than a 1 kilo or 2 kilo drone hits your face. So so that is like, I think safety, that is a major thing of why the Crazyflie is still so small, and why people use it within like, their control courses, their robotics courses. Yeah.
Okay, makes perfect sense. And also, it's is a niche that I don't know if somebody is exploiting that niche, which is about the smaller drones that can be carried very easily. You can buy several. You can bring to the student and provide several to the students, not only one big one that you have there, and everyone has to take turns. It's very good idea. And which sensors has the Crazyflie?
So the Crazyflie itself has some basic sensors. So it has an IMU, inertial measurement unit, with a gyroscope, accelerometers, and a barometer. Must say that the barometer is a bit tricky to work because it's like a bare PCB with wind, and barometers don't really like that apparently, because like a lot of pressure changes with wind.
Yes.
So that is already enough sensors for the autopilot to be able to do manual flights, that you're able to control it by some with a controller, things like that. But the nice thing is that you can actually add sensors. There's this practice of expansion decks, so you can add decks to it that has different sensors on it. So like for instance, yeah, if for instance you want to use a certain positioning system like ultrawide, then you can put a deck on there that um, has that module on there. We have, for instance, like a deck that has a couple of laser range sensors, so you can do some obstacle avoidance with it. We also have a deck that has a camera on there with some extra processing capabilities as well, called the AI deck. So yeah, so that you're able to kind of like add more sensors to it for whatever application you would like to use it for.
But then if you keep adding sensors and stuff, then it will be heavier, and also it will be requiring a lot more of energy from the batteries. And then, so what autonomy has a Crazyflie without any expansion deck?
Without any expansion decks, if it's purely only the IMU, let's say that reckoning is very difficult with the accelerometers alone.
Oh,
So at least like with accelerometers that are as so close to the motors and so affected by it. So if you don't have any expansion decks, it's mostly suitable for manual flight. However, if you, for instance, add something we call a flow deck, so you have an optical flow sensor and a range sensor on top, then actually that camera is able to detect the difference between one picture to another. So then it's able to kind of like see the flow in time, and together with the range sensor is able also to not only control its height but also kind of determine on what its velocity is at that moment. And of course with integration, then you have some kind of relative positioning. So at least in positioning, that's kind of like the most basic type that you like deck that you would need for autonomy.
okay.
That's like you need that. But of course, so like that's kind of like the optical flow is more closer to like the dead reckoning with wheels for ground robots, let's say. It also has drift, obviously.
Yes. It's like an odometry, a raw odometry computation.
Exactly,
right?
yeah. It's kind of like it's visual odometry to be
Visual
exact.
odometry, yeah.
Yeah. But of course, if you only have an optical flow sensor looking down, you're pretty blind as a Crazyflie. So like if anybody would come to me, it's like, okay, what is the basic package that I should have to do like any form of robotics? I would say flow deck and multi-ranger.
Okay.
Because with the multi-ranger, you also have to be able to do obstacle avoidance and a little bit of mapping as well, if you like that. So it's like, then at least you have something that's able to take off, to be able to fly still, to be able to go from A to B, and able to detect if something is in front of it or something on the side.
On the side.
And then then it actually becomes, instead of something that you only control manually, to something that is more closely related to a robot.
Okay. And then, so first, I think that you should be put into the business department, into the selling department instead of the development, because you just sold us the complete stack. So I want to buy the full stack. Okay, so
And this is just the most basic stack.
and that's the basic.
But,
Okay.
but
Second,
sorry.
About the battery life then.
Mm-hmm.
With this stack, how much time of flight can be the drone?
With the battery that we provide now, it's about 6-7 minutes of flight time. And as you mentioned already before, there was a very good comment of you. The more decks you add, the less time you have. Of course, because weight has a very big factor on the total flight time. The amount of energy that the decks or the sensor require have a lot of flight time, and it's unfortunately not a linear relationship. Like if you're at the very end of it, it's like when things start to decrease very quickly.
Okay.
So
like 2 minutes or 3 minutes.
Well, yeah, something like that. So I have we are soon going to offer more upgraded batteries, so you're able to extend that flight time. like when I was doing my PhD, I was using the Crazyflie. I found batteries also somewhere else. They weren't like fitting very nicely, but they were a bit bigger. And then I got a flight time for 10 minutes.
Okay.
So, but I must say it's there's kind of a beauty to it, right?
Why?
Like, you know, you have such a small platform, you only have limited resources. You really have to choose which sensors you can use for autonomy and what is the lowest, like what is the least minimal like necessary for a decent autonomy.
I
Then
see.
compared to if you, for instance, have like ground robots, you can pretty much do whatever, right?
Yes, yes, yes. For
So
many
like,
hours, yes.
yeah, so that's like, you know, there's frustration, but there's also beauty behind it, let's say.
Or you can buy more than one. So when one is recovering, then you can practice with the other one. So maybe let's say, how much does it last? I mean, how much does it take to recharge a Firefly?
Yeah, I
Crazy
think
fly,
it takes
sorry.
about 30 to 40 for 30 to 40 minutes.
Okay, so then you need
Um,
four of them. So you will have a 4 rotation. Hey, that's another selling point. So you are fully selling full stacks 4 times now.
yeah, I guess like you can well, if we're on the selling tour anyway, we also have these decks that you're able to charge do wireless charging.
So you can, for example, let's imagine that I want to construct here a remote lab app for our students. Then they come, they use the robot, and then when the session is end, is a 10-minute session, let's say, because we have optimized for this. Then when the session has end, then the robot can go and charge itself on that
Yeah,
wireless charge. Oh, that's awesome.
absolutely. Yeah, that's actually our go-to demo that we show like at ICRA and IROS, is that we have this like, yeah, let's say we have this fully autonomous demo where we just have like a bunch of Crazyflies with on these charging decks. And then like based on their battery level, like, oh, I'm charged enough, and then one starts flying and the other one starts
Uh-huh.
flying, and they try to avoid each other. But they, when their battery is a little bit like less, they go back to the charging pad and then let another one take off. So yeah,
Awesome.
absolutely. And there
Awesome.
have been labs built with Crazyflies exactly on this principle. So
Awesome. 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 Excellent. So, okay, so I have to check that one for our students. Excellent.
absolutely.
And then, so for the, you mentioned that the Crazyflie it runs at present, it already can run ROS1. So there are the drivers there, and you are preparing the ROS2. Okay, so you already mentioned about that. Then how about your usage of the Crazyflie? So what do you use the Crazyflie for?
So what we internally use the Crazyflie for is like you know, we are all busy with making the tools for the users, let's say. We are making like the API for the Python library. I'm more like working on like, you know, making the simulator for ROS, things like that. We're making the tools to make it easier for researchers
To
to use
use?
it. Um, However, like when I was doing my PhD, I was on the other side of it, of course. I was at
Uh-huh.
the side of the researcher who
Of the,
actually had to do something with the Crazyflie. And like during my research, I had to, yeah, I had to make them fly fully autonomously indoors without GPS. Had to make them explore an insights like, you know, in indoor environment all by themselves with about 6 of them. So it's all, I would call it a swarm.
okay, a small
But
swarm of
yeah.
6, yes.
So and so that's I was then the researcher at that time. So I was actually doing the cool stuff. Doesn't mean that we don't do cool stuff in Bicraze. Like we actually make some really cool demos where we can show that like, hey, you can use it for this, or hey, you can use it for that.
Yeah.
But when I was on the receiving side, that's kind of like, you know, that's what I was using it for like showing that autonomy is possible on these small platforms.
Uh-huh. Okay, okay. And with a group of them, so that they collaborated. So that was your swarm drones research about. It was about the collaboration between different different quadcopters, and in order to explore an environment.
Yes, yeah, that was indeed the case, and The challenges is that they were not able to use a central computer because they had to fly pretty far out, and communication can only take you so far, let's say. Like they also need to they also have to keep navigating when they lose touch with the central computer. So it had to be like full onboard autonomy if they would sense one of the other drones to come near, if they would come near, which I implemented at that time was based on their signal strength. They will send out like, radio signals to each other. And if one of those radio signals usually have something called, yeah, some kind of signal strength to it as well. And if is strong, that's like, there might be another
Around
drone
here.
nearby.
Uh-huh.
So that's kind of like how they very basically communicated with each other and moved out of the way. Yeah, so and the goal was to explore, and when they're on half of their battery,
Mm,
they also had to be able to return to their home location as well.
okay. Okay, so they need to know also their own location in the whole map, the whole area, right?
Yes. Yeah.
Okay. And then if based on that radio signal, that was every one of the drones has had its own radio identifier. Let's say all of them, they are different, so you can see each drone can identify the others based on the radio signal that they are receiving. So if it's in this frequency, that means that is the George. If it is in this, the quadcopter George, and then if it's something like that.
Yeah. So it needs something like that. Like they have to kind of sometimes also communicate in different frequencies for, yeah, I guess like in communication you want to reduce the like packet collisions, let's say.
Yes, definitely.
They also had their IDs with them, so they had like a basic rule, like if one of them had a higher ID or the other one had like a lower battery, had always right of way. So yeah, but of course, if you want to do, the challenge is that they knew that another drone was in the neighborhood, but they didn't know where exactly.
Exactly. Okay.
Yeah, so they had to kind of like move away because they were navigating based on wall following.
With
So that was,
infrared sensors.
yeah, exactly. So what they would do is actually kind of move away from the wall until the other drone has passed, and once the RSSI or the signal strength becomes a little bit more weaker again, that's when they are continuing. So that's yeah, that was kind of like, but they didn't know exactly where the other drones were. So
Okay.
yeah.
But then I don't know, there's something that I don't understand. Have you seen, probably you have seen those spectacles of hundreds, I don't know how many drones they are there, which are amazing. They can do even figures in the air that are moving. So based on the lights and change, but then how do they communicate in those swarms? How can they coordinate and know about the distances of each one of them, the relative position between them?
Yeah, I'm going to completely speculate about this, of course, but what
Okay.
I think what they're doing is, at least like for at least maybe not the super massive drone shows, but maybe maybe just the normal ones, is that they do all communicate their own GPS position back to a central computer. Or yeah, there's also this positioning system that they use for outdoor flight called R2K. I don't know what the abbreviation stands for, but it's because GPS is like 3 meter accuracy and 3 meter accuracy. So,
Yes,
but
exactly.
those drones are a lot more tighter format than that,
Yeah,
right?
very
So
precise.
yeah, so they might be also using positioning system called R2K. So
Oh,
that's,
okay.
but anyway, they have then onboard positioning that they would need to probably communicate to some kind of remote server or remote computer that is able then to coordinate the drones with each other. So that is kind of completely centralized. However, I would imagine, and I'm not sure exactly because I haven't really like developed any show like this before, is that as at one point you come to critical mass where you cannot really do that anymore, with that much of communication and radio packets getting lost and delays and everything. So they must be able to do something with peer-to-peer communication, or whatsoever. So
Between
yeah,
them, right? Between them. So they
yeah,
create their own network between them. Not
yeah. At least
one.
that sounds like a smart thing to at one point. Like if you hit a swarm that's big enough, then just communicating everything back to a central computer is just going to, yeah, not be worth it anymore.
No,
Let's
no, no,
say.
no. Yeah,
Yeah.
yeah. Makes sense.
So
Makes sense what
yeah,
you mentioned. Yes.
yeah.
And also to detect, so to correct errors. So if you can understand the positions of your companions around you, then you can correct your position related to all of them to devise the pattern that they have to. So it's not somebody, a central position that needs to do, you have to be in this position, but instead each one knows the relative position with respect to the others. And then they communicate between them. That makes sense. That makes sense. Okay, so we have to investigate more because I didn't know that exists this positioning system for positioning somebody in 3D in the how do you call it, this one?
Yeah, so from like the R2K, that is
R2K.
kind of like a R2K is like an outer positioning system that they use to kind of like, correct the errors that you have in GPS.
Okay.
So you have a more accurate location. Indoors, you have a whole wide range of positioning systems as well. I think the most commonly known is motion capture systems. It's mostly also used for ground robots. However, well, yeah, and of course, relative positioning systems, that reckoning, visual odometry,
Yes.
like that is
Typical
of course like
robotics ones.
exactly. We actually support 4 different positioning systems for ourselves. So we also have the Crazyflie is also able to use a ultra wideband system. I don't know if you've
No.
so ultra wideband is also kind of like, it's also a way of communicating with that uses a very wide band or wide spectrum of frequencies, let's say. However, like in practice is that you have one ultra wideband node here, you have the other one here, and you're able to detect the distances between them. And usually it's up to 15 centimeters. And so if you place a couple of like these ultra wideband anchors and you know the positions of those anchors and you have one of the
On
like
top.
tags on the drone itself, then yeah, it's able to kind of also determine its own position, like in a similar sense like GPS almost,
Yes,
right?
exactly. It's a
Yeah.
local GPS.
Yeah, exactly. So those are ultra wideband systems. We call it in the Bicraze ecosystem, it's called a local positioning system, but there's multiple options out there of different robotic systems. Another really cool one, at least that we're using right now, is the Lighthouse positioning system, which comes from virtual reality.
Uh-huh.
Because yeah, these headsets like from Valve or anything like that's able to position yourself in this
Yes.
virtual environment.
Yes. Like augmented reality system.
Yeah. Augmented reality, virtual reality. So you either have like the Oculus Quest that's able to do that with like some SLAM algorithms from like completely on board, which is also really cool. But you also have systems that have like special base stations in the room that has like these laser plane sweeps that are just like that's let's say these virtual reality goggles are able to detect, and it's able to determine its own position in the room.
Yes.
So yeah, we actually reverse engineered that for the Crazyflie.
Okay. Excellent.
So yeah. So it's so that's also a really cool system. We always use it for demos as well, and it's close to motion capture system accuracy, but perhaps for a smaller volume. And it's also slightly cheaper as well than mocap systems as well. But it's yeah. So anyway, for a drone to know its position is very important.
Okay.
But there are
Yes.
multiple options for that.
Okay. Yeah, I see. That's a point that I didn't know. So for us, the robots. So we are one of the first things that we teach is how to localize a robot in a place, because we want it to go from one place to another. So for that, it needs to know its position in that environment, right? And then, of course, for drones, it's the same. But the only thing is that it's a lot more complex, right? Because you cannot have so many sensors on board. if you could have a laser, then that would be very cool, because then you can apply 2D techniques, 2D mapping techniques, and then localize. But that's not the usual way, right? Because it's so heavy, and also so consumes the battery in just I suppose.
Well, you do like as long as the quadcopter is big enough, you can carry the right tools for that. So it is possible to do 3D localization with only the onboard
Sensors.
sensors. Let's say in a lidar base in very similar fashion as with ground robots. But those drones are usually, in the 2 kilo, 3 kilo range. I think the only problem is that like ground robots can kind of like look around, right? They can kind of explore. They don't need to know exactly their location yet. But like, after a few meters or so, like, then they have already figured out. A drone needs to know its position right away.
Why?
Because as like a quadcopter is an unstable system, and you don't want it to start drifting and crashing into a wall. Because if it doesn't know its position at that point, it's not able to control it.
I see.
So that's why if you want to use like slammer, usually that takes a while before you're able to have a stable position. It maybe is better to maybe take off and do visual odometry, for instance, first. That's usually what they use to make it stable. And then maybe you can start to like, the 3D mapping with the lidar or 2D mapping with the lidar of the environment. But yeah, that's why like position is like, it's key. You need like, it already needs to have a good position from the get-go.
Okay. And then for the basic system that you sell with the 5 flyers, so that would require to have also a positioning system, right?
So the flow deck is, I consider also a positioning system. It's just an onboard positioning system, because so like you're able to then, based on optical flow, then whenever you start the drone, let's say with an optical flow sensor and range, that's where the 000 position starts.
Yes.
Yeah.
Is the odometry 0?
Yeah, exactly. So but however, that is relative positioning. That is not a global positioning. So that is something that you then have to solve by, for instance, if you have the multi-ranger on there, and there have been papers that have made like, like now I'm talking about the Crazyflie, of course, but there have been papers that actually are able to do some very basic type of slam and able to do like, able to do the positioning based on that. But so that is already something that you can do basically with like an optical flow sensor, range sensor, and then range sensors that's able to look into the environment. Yeah.
So
but
would you say that the challenges at present for drones would be in localization positioning systems?
I would say perhaps like, improving the relative positioning systems, or the autonomy of that. Global positioning systems, there's already so many options out there, like mocap, the ultra wideband, the lighthouse positioning system, and there's actually many more that people are still developing. So I think that is something that has already been figured out. The thing that needs to be developed more is that have drones that are able to rely perhaps a little bit less on those systems, and if they're big as well. So yeah,
but what would
which
it
can
mean
be done by optical flow.
I'm sorry. So what would it mean to rely less on those systems? It would mean that they will kind of know where they are independently of all those systems in a fully autonomous way. That's what you mean?
Yeah, I think like in terms of autonomy, autonomy, it needs to still come to a level that's a lot of ground robots are still at. Like you have systems out there, but I think like if you just look at like the paper density on that's where a lot of the work is still on. So to have like GPS denied environment navigation, that is a very challenging way. There are techniques, of course, to do it, but it's like, it's so much easier if you have a global positioning system. But if you do like a search and rescue scenario with a drone, then it needs to do pretty darn well without. However, I would say, like, if you look at, for instance, like the DARPA subterranean challenge, where they had drones actually navigating through like a whole, yeah, the full cave system, let's
cave,
say, with
yeah, exactly.
like and working together with like, you know, walking robots or ground robots, like, you know, it's yeah, I think perhaps I'm being a bit more overly negative than what the actual state of what they can already do. But it's
Okay,
at
I
least for
don't know.
beginners, it's definitely a lot more difficult.
Okay, well, I don't know. So you are the expert. So we are taking your words very, very seriously because you know a lot more than us. So we respect. So if the situation is negative, then that means that there's an opportunity for the listeners of the podcast, because there is still space so where we can innovate and we can create something interesting that improve the sector. So there
Of course, yeah.
there are listeners of the podcast. There you have some opportunities there. Then
Yes.
let me ask you one final. Two final questions. So first one is that I saw that you have restarted recently the ROS aerial meetings. What are those?
Yeah, so as I think you've already said before, like ROS seems to be very underrepresented for UAVs, and that's absolutely right.
Yes.
And I've been already wondering, I was already wondering for a while for like, why is there not a ROS community or working group on aerial robotics at all? Like there's one for marine. Why is there not
Yes.
one for aerials? It's like, you know, it's yeah, it didn't really make sense to me. And it was yeah, it was actually at ROSCON in Kyoto that I met with the Peaks for Drone Code Foundation, Ramon Roche, and we just kind of started talking to each other, like how to collaborate and what is a good common ground. And it's like, yeah, we're at ROSCON. Why not ROS?
Yes,
So
exactly.
that's why, yeah, that's how kind of like the ROS Aerial Community Working Group is kind of a joint effort between Bicraze and the Drone Code Foundation. And yeah, and I think we've had like 8 meetings so far. It's kind of still in the phase of that we have a lot of topics to discuss. Aerial robotics is very wide, so there's a lot of things to discuss, like where we would like to focus our efforts on. And also we're inviting people that are using ROS in their aerial robotic projects to kind of present their work. And then we hope to come to a state at one point once we gathered all of that information to be able to have clear development goals to maybe improve, for instance, like education, or perhaps like have like a joint effort with more parties to make a turtle drone, let's say,
Okay,
because like, you
turtle
know, a
drone.
standard hardware for like, of course, I'm biased towards the Crazyflie, but I do agree. It would be much nicer to have a platform that can actually run full ROS on board
Yes, that would be
for people to
awesome.
actually learn.
Awesome. And
So
that, I think that the direction that you mentioned about micro ROS, I mean, I think maybe that's the direction to go in order to achieve that, maybe.
yeah, exactly, yeah. But I would say as like, you know, in a turtle drone scenario, it will probably be a bit bigger drone, let's say,
Uh-huh.
with an like, you know, flight controller, companion computer. Yeah,
I see, I see.
we just have to figure out the safety part, but
Yes. Okay. Yeah. Okay. How to protect and all that. Okay. Yeah. So, well, you can figure out for that. I think
yeah.
it's a cool, super cool idea. The turtle drone you mentioned, right? You said turtle
Yeah.
drone.
Yeah, let's hope it will come into fruition. But that's the eventual goal of the ROS meetings. The ROS aerial meetings is to make it like, you know, yeah, to have more of a marriage between from ROS and aerial robotics.
Robotic.
That's
Yeah. Okay. And
yeah,
it
that is
does.
the way.
Can anybody join those meetings? Are they open to the public? Anybody
Oh yeah,
interested?
absolutely. Like it's a community working group, so it's like, you know, we can just like anybody can join and join the discussions. We haven't started any development groups yet, but hopefully after ROSCON New Orleans, we'll be able to maybe pick out some topics that really need our attention right now.
Okay, great, great. And for the audience of the podcast, so guys, if you are interested, you can join. You don't have to say anything; just listen there and attend, and then bit by bit, you will be more engaged and decide to propose. But you don't have to. But you can attend. Okay, so if you are interested in this subject, ROS in aerial vehicles, then you can go to the ROS aerial meetings. I will put a link in the show notes for this to go there. Final question. So what are your future plans for Crazyflie?
Yeah, so in terms of hardware, so we're hoping to soon also release a Crazyflie that's able to carry a bit more.
Okay.
Yeah.
Same
So
size?
like
Same
we've got
size drone?
yeah, same size, like brushless motors is the idea. So we're kind of beta testing that. And also we have already given some more upgrades of like, better propellers, more efficient propellers, more motors. And we also have like a couple of ideas for new expansion decks as well. But I think in the coming years, for sure, we will have an upgrade of the Crazyflie, like the Crazyflie 3 that has an upgraded microprocessor and is also able to do. So yeah, we have a lot of ideas in the pipeline.
Excellent. So if
and
you
and
can share one of the secret ones.
the secret ones.
Yes, you have.
I'm secretly hoping for, we need a camera Wi-Fi deck,
Okay.
so like more of like because the AI deck has a camera on it, but it's more like lower resolution and it's black and white. So it would be nice to have like more of an HD Wi-Fi camera on it, so
That would be awesome.
you can actually do some proper off-board and navigation with OpenCV and ROS, obviously.
Okay,
So
of
yeah,
course.
so that I think in terms of making it really a tool for education in that sense, that is what I'm hoping for.
Okay.
I'm going to push my colleagues to work a bit harder on this.
So keep us posted about that. But
Yes.
I also think it's a very, very, very cool idea.
Yeah.
Very cool.
And also it's not completely secret. Let's say, if you come to any of us at conferences or anything, like we're more than willing to share any of the ideas that we have. So
Okay. Just wanted to make it more spicy, the podcast.
Oh, yeah,
No, that's the secret one. Only
very
for
secret
for
Wi-Fi
the ROS
camera.
Developers podcast,
Yes.
Okay, I have another question for you. It's not here, but by curiosity, because you mentioned, so we can say that you had your PhD just a few years ago, right? 2019. So, but now you are working as a developer. So how do you feel this difference between changing from a researcher and now working as a developer? I think that could be interesting for the audience because it's the ROS Developers podcast. So maybe, what do you think about this? So do you miss your researcher days? Do you love your developer job now?
Yeah, it's a good question. Yeah, when I was doing my PhD, it was like, it's the academic world. You write papers, you do the experiments, you make sure that the experiments work. So it's like, you kind of do it for your papers and your thesis, but you don't perhaps do it for like the maintainability of your code. Once I became a Bicraze, I actually really learned how to be a developer, how to make maintainable code, how to work with CI, how to how to be able to have something that other people can reproduce. And that is kind of like a very, very different, it's a very different world, but I'm still working with so many other researchers that I'm still having the best of both worlds. I don't really necessarily have to write papers anymore, but I still can work together with researchers to achieve, whatever they want to do with their research. And also I co-organize, for instance, also a workshop, like the role of robotics, the role of robotic simulation in aerial vehicles, the ICRA 2023. And that was also like my co-organizers were researchers as well. And so I'm not completely out of the academic world, Russ.
I see. So you managed to combine both of them, right?
Yeah.
Oh, excellent.
Yeah, exactly.
Lucky you.
And it's a lot of fun.
Yeah, lucky you. Okay, then, that's all. So we have been here for a long time already. So thank you very much, Kimberly, for all the insights and all the information that you share with us. Thank you.
Yeah, you're welcome.
Okay. And then, so that's all for today, people there. So thank you very much for listening to the podcast. Remember, Give us 5 stars in all the platforms that you are listening to this. If you have some suggestions, have a look at the show notes to get an email, and then you can send us your suggestions. For example, the control of the volume, that sometimes I don't do it very well. So yeah, I got the message and I'm trying to improve it. So any other complaints, any other ideas, share it with us in the show note email that I have put it there. And that's all for today. See you next week with a new lesson from the expert. And until then, keep pushing your ROS learning.